Hi, I'm Matthew Martin, and this is my DS4100 final project. For my final project, I will be exploring the wine industry and how it rates wine. Wines are currently rated on a 100-point scale. These ratings are determined via taste tests by certified sommeliers. This can lead to many problems due to the subjectivity of the process. In addition, to what extent does wine rating have on its final sale price and essentially its value or worth? Most wines are ranked on the upper portion of the 100-point scale, leading to inaccuracies in ratings and individual perceptions. To combat these discrepancies, I want to explore other potential methods of rating wine and see if wine prices and sales are actually affected by ratings. In addition, try to discover what other factors play into the final sale price of wines and how these factors may influence their rating scores. Through my research, I have found that physical-chemical properties of wine can be used to detect the quality of wine. This can create a more streamlined and normalized process for rating and pricing wine. The physical-chemical datasets were collected from the UC Irvine database. It contains numeric physical-chemical data of 11 properties for red and white wine. The wines spawn from the Minho region of Portugal. The qualities are based on a scale from 1 to 10. The sales and review dataset was collected from an online blog that was culminating information of wine sales in the United States. The data was extracted from the Tableau data program on the site since the original files were decrypted. The data consists of wine sales from 2001 to 2014 of 47 different grape varieties and 15 countries. Now that we have completed our business understanding of the topic, we can move into the data preparation phase of the CRISP-DM pipeline and explore the physical-chemical data. For the red and white wine data, the summary of each of the factors for both wines can be seen. In terms of distribution, for the most part, it seems to be normally distributed for both wines. There are a few factors that are distributionally skewed or not distributed at all. For citric acid of the red wine, it seems that there is no shape to the data and that is pretty constant throughout. Distribution of total sulfur dioxide, sulfates, and alcohol for red wine seem to be skewed to the right. Each contain outliers but are barely visible. For the white wine, in terms of distribution, for the most part, it seems to be normally distributed for each of the factors. Citric acid and density seem to be skewed to the right. Each contains outliers. For alcohol, it seems that there seems to be no shape in the data and it is pretty constant throughout. All contain outliers classified to be anything that stand outside of 3 standard deviations of the mean. Here, we will see the outliers for the red and white wine datasets. The NAs indicate the outliers. For the red wine data, there is a somewhat strong positive correlation of 0.48 between quality and alcohol, a somewhat strong positive correlation of 0.25 between quality and sulfates. For the white wine data, there is a somewhat strong positive correlation between quality and alcohol as well of 0.44. Also a somewhat strong positive correlation between quality and sulfates of 0.25. There's also a somewhat strong negative correlation between density and alcohol of negative 0.78. Based upon these heat maps, it seems that alcohol and sulfate levels have the most impact on increasing the quality of wine no matter if it's red or white. Now that our data has been normalized and prepared and interpreted, we can move into the modeling phase of the CRISP-DM pipeline. To predict the quality of wines based upon physical-chemical data, I will be implementing the K-nearest neighbor or KNN machine learning model. KNN is a non-parametric model that is neither affected by the distribution of the data nor outliers. The model uses the Euclidean distance between unclassified cases and known training cases in order to determine the nearest neighbors. To get an accurate calculation of distance, the data needs to be normalized to a similar scale. My KNN model calculates all Euclidean distances for the test case compared to all training cases. These values are then put into a vector that is created in the training set. The training data frame is then ordered in ascending order by Euclidean distance. Then the mode of the indicated K value of closest neighbors is the calculated prediction for the test case. For this, I implemented the KNN predict, predloop, and best K functions to implement the KNN model on the red and white wine datasets. Predloop calculates the prediction for each case in the datasets and stores the results in a vector. Best K tests every K value from the square root of the cases, the training set, up through 5 times of that value. From here, the accuracy of each model with its respective K value is stored in the data frame, and the K value that yields the highest accuracy is returned with the respective accuracy. Model, I will split the data into 80-20 of training and validation sets. Here's me running the code for the K&N predict method, and here's the code running for the K&N preloop method. And now I will implement the best K, which will return the best accuracy and K value for the two K&N models of the red and white data sets. For a few minutes, the results return that for red wine data, 22 nearest neighbors were used with an accuracy of about 42%. For white wine, 50 K values of nearest neighbors were used with an accuracy of about 39%. These will vary based upon how the data is randomly split. Although these are not amazing results, they are not the worst. This may be due to the amount of data available not allowing for the training of the model to be as developed. In addition, potentially there could be better scale normalization technique that could be implemented instead of using z-score normalization. Potentially another method such as min-max normalization could be used. Now we will go back to the modeling phase to implement logistic regression. Next, I implemented a logistic regression model to predict if a wine is red or white based upon its physical-chemical properties. As for the accuracy of this logistic regression model, there was a 0.99 accuracy. This is a really good fit for the model. The amount of false positives for red wine was about 0.17 and 0.22 for white wine. Although there is a slight bias towards predicting red wines, this leads to the conclusion that the model does not include significant bias. Now we will go back to the data preparation phase for part 2 of the project. We will import the sale and review dataset, subset it so that only significant factors and non-superfluous factors will be included, and subset it by grape variety so data exploration can be more efficient and successful. Has been imported. We can see that there are missing values for rating score, region, and year. I will impute these values using the mice method and use predictive mean matching as a form of data imputation. I will now run the data imputation. Now that the data has been imputed, you can see that there is no more remaining NA values. From this, we can graph the data to see the distributions. Final price and regular prices, as seen here, are heavily skewed to the right. Rating scores are slightly skewed to the right, but less than final price and regular price. Now that we have interpreted and prepared the data, we can start to build our models. First, we'll start with a linear regression model. First, I will implement a simple linear regression of final price. The only factor included will be rating score. I will now run the simple linear model. From this, we can infer that rating score is a significant predictor for final price from this linear regression model. I will now implement a multiple linear regression model for final price. I will test the full model and see how statistically significant all factors are, and then I utilize the step method to use backward elimination to get only the most significant factors that remains. I use the step method as previously stated, and that gave me with the final model that contains rating score, wine name, year, and regular price. This also contained a adjusted R² equal to 1, and for the mean squared error, I will run it now, is about 0.012. I'll plot the residuals against the rating score to test the fit of the model. As you can see, all residuals are within 0.1 of 0 and are randomly scattered throughout the plot. This infers that it is a good fit for a linear regression model. After modeling and evaluation, we can now move into the final phase of the CRISP-DM pipeline, which is deployment. Here are some conclusions made from this project. Based upon the fact that rating score is a significant factor in deciding and predicting the sale price of a wine, More accurate forms of ratings, such through methods as physical chemical properties, should be implemented into the industry. More studies will need to be done to collect more data on physical chemical properties. In addition, we need to train the models with more data to make accurate predictions of future wine sales and ratings based upon more streamlined and normalized factors in the wine industry. Thank you for your time, and I hope you enjoyed this presentation.